Isabelle Horvath now, and she worked on a project with Casey Godwin, Craig Stowe, Tim McGuire, and Sally Petrella. Welcome, Isabelle.
All right. Thanks so much, Mary. And thanks to everyone for tuning in. As Mary said, my name is Isabelle Horvath, and I'm joining the Sigler Fellowship this summer from Marquette University, where I'm currently a PhD student. And this summer, I worked to build a socio-environmental urban water quality model with citizen science data. In this presentation, I'll go over the Rouge River, which I studied in this project, data used for the project, our modeling approach and results, and some interpretation. So we're all pretty familiar with the Great Lakes, but where's the Rouge River? The Rouge River lies in southeast Michigan, just southwest of the city of Detroit. And the Rouge River watershed is a fairly large and urbanized watershed. It drains about 1,200 square kilometers into the Detroit River. And if we take a look at this figure on the right, we can see some heterogeneous land cover in the Rouge River, where you see lots of red, indicating urbanized land cover, and it becomes especially dark and concentrated, showing heavy urbanization in that southeast corner as we get closer to downtown Detroit. But we also see some mixed land cover where there's some agricultural land over on the west side of the watershed. In addition to being highly urbanized, the Rouge River watershed is also highly populated, with about 1.3 million residents. And with such a highly populated and urbanized watershed, it's important to think about protection of the watershed. This is the mission of the Friends of the Rouge non-for-profit group. They aim to restore, protect, and enhance the Rouge River through stewardship, education, and collaboration. And one way that they're able to do this is by monitoring river quality through benthic invertebrate studies. This program started in 1998 with a grant from the Michigan Department of Environmental Quality, where they were using benthic macroinvertebrates as bioindicators of river quality. Friends of the Rouge adopted this program in 2001 and made it part of their regular programming, running a biannual bug hunt event from 2001 up to the present. But what is a bug hunt and how does that relate to stream water quality? We're able to use benthic macroinvertebrates or water-dwelling bugs as bioindicators of water quality. And the way this is done is trained volunteers go out into the Rouge River twice a year, where they can look to collect benthic macroinvertebrates with nets. They can pull samples over to the side of the stream, where they're then categorized and organized. This leads to a lot of qualitative information about the different species and diversity in the Rouge River, which can then be translated into a stream quality index using one of these data sheets made by the Michigan Department of Environmental Quality, where first different benthic macroinvertebrates are identified and categorized based on their sensitivity to pollution, where species might be pollution sensitive, somewhat sensitive, or pollution tolerant. Once identified, species are grouped as to whether they were rare or common at a specific observation site. Then this combination of pollution sensitivity and the rare or common nature of the bug is used to enumerate from our qualitative information about the benthic macroinvertebrates into a more quantitative score called the Stream Quality Index, where a low score, or a score in the mid-teens, indicates poor water quality, and a high score indicates excellent water quality, and that might look like a number in the mid to high 40s. So now that we understand what the Friends of the Rouge are doing with their citizen science data collection, how are we using this information? To answer the question, can environmental and social data be used to model SQI in the Rouge River? And what do bug hunt results show about Rouge River water quality? We look to answer these questions by using three different groups of data. First is that citizen science data collected by the Friends of the Rouge. This data indicates stream water quality, which is what we're trying to model, so it's our response variable. SQI data was collected from 2001 up to the present, so our data set ends in spring of 2021. There were 41 different temporal observations as data is collected twice per year. And we have 122 different sites where data was collected. But not every site has the same number of observations. So to deal with this, we just took an average of every observation to occur at the different sites. Taking a look at this SQI information, we noticed that it was skewed data. And also, SQI can only range from the mid-10s to the upper 50s, so we know we can't have negative values. So we took the log of this SQI data, and this is what we work with moving forward. Our second category of information is environmental data, and this comes from the EPA database called StreamCat. This environmental data is geographic or other environmental data that can be useful in describing the quality of the river. Some examples of this are stream chemistry, stream temperature, and land cover data like forested land or developed land. Then our final data set is social information, and this is collected from the US Census Bureau, where we're adding social information to try to have a better understanding of the connections between human-derived variables and water quality. Some examples of these variables are racial information like the Black, Hispanic, and Asian populations, as well as people living under the poverty line and median household income. When we're looking at those explanatory variables, that environmental and social data, there's a couple of different ways we can look at it. And if you're familiar with hydrology, then you might know these terms: a watershed, which refers to all of the area that drains into a water system, or a catchment, referring to just the drainage area to a specific segment of a river. Well, in our project, we had to alter these definitions slightly because we're looking at information collected at a specific site. So a catchment stays the same, but for us, when we refer to a watershed, we're really thinking about all of the catchments that are upstream of a specific collection point that would have drainage areas that lead to that site. So now that we understand what data we're working with and the different formats it's in, let's take a look at our modeling approach. We first combined all of the possible variables from the StreamCat database and the US Census, which led us with hundreds of variables. So we had to apply a logical filter, getting rid of things that just didn't make sense for Southeast Michigan, like proximity to mines or if there was volcanic activity. And this left us with a few dozen variables to work with. We then eliminated variables by using simple linear models to select just those variables that were significant with SQI. And we plugged those chosen variables into spatial models, where we have two different formats of spatial model. First, models that are looking at just environmental data or data that's coming from the StreamCat database. And then looking at models that are both environmental and social, so combining in those census database variables. So all four of the models that we're using are spatial models. So what does that mean and why did we use them? One of the first rules when we're modeling is that you have to have independence between sites, but we violate this when we're thinking about a river system because there is dependency between the different observation sites. One way to encompass this dependency is by using a spatial model. And the USDA and US Forest Service developed a product that does exactly that. It considers the spatial relationship between two different points. And there's two ways that we can have a spatial relationship. First, having a flow-connected relationship where two sites might have a direct flow path between one another. And second, through a flow-unconnected relationships, where two sites might be physically close, but not connected via a flow path. And by encompassing this spatial information, we're able to take scattered observation points around a watershed and translate them into a different predicted value for every segment in the watershed. So now that we know we're using spatial models, how do we compare the models we're working with? We use the evaluators of an R-squared and an AIC, where we're looking for a higher R-squared and a lower AIC to show better model fit. As we're building our models, we're looking to fill in these generic equations, building a model that can explain the log of SQI using just environmental data, and then trying to contrast that model with models that use both environmental data and social information to try to tell us whether social information can help us to better explain water quality. So what did we find? First, we pinned down what our most important variables were, where we had 2 environmental and 1 social variable. The first was impervious surfaces, where this is the percentage of land cover that can't absorb water or is impermeable. Our second variable is the sedimentation clarity, which is a modeled value between 0 to 1 that represents a lot of different things, like the slope of the land, the soil type, channelization, and uses all of those to try to estimate how much sediment might be in the river. Our third parameter was the percentage of people that are living under the poverty line. And it's important to note that all 3 of these variables are most significant in their upstream watershed version. We could then plug in these variables to our various models, where first we're looking at just the models using environmental data, and that was our sedimentation and imperviousness variable. Then we could build up a model that uses those same 2 variables, but also considers a random effect or a logical grouping, where we were trying to answer the question of, do streams have different behavior if they're a low order, like a first order stream that doesn't have a large contributing area, versus a stream that has a larger contributing area or might have lots of other streams entering into it? And we didn't see much change between the multivariate and the more complex random effect model. Then we can add in our social variables to compare how the addition of poverty improves the model, where we see improvement in both our R² and AIC parameters. Then we try again to look at how stream order would affect, and we don't see any improvement moving from the multivariate to the random effect model. And that transition adds a lot more complication into the model. So it makes more sense to stick with our multivariate social and environmental model, which had the best performance and lowest complication. So our final model uses imperviousness, sedimentation clarity, and poverty. So how important really was that spatial modeling that we did? This figure helps to show how much better a spatial model outperforms a simple model, where on the x-axis we see the observed water quality, and on the y-axis we see what our model predicted. And both of these are showing the same variables built in the same model, where the figure on the left shows the simple and the figure on the right shows spatial, which encompasses the relationship between sites. A perfect model would predict values along a one-to-one line, or the exact same prediction for each observation. So when we see the tighter cloud of points on that spatial model, it's showing that that model performs better. So we finally arrive at our plugged-in variables for that generic equation we started with, using both social and environmental data. And this model can tell us some information about water quality in the Rouge River. First, we learned that with a 0.1 increase in sedimentation clarity, SQI would increase by 9%. So this is a little bit hard to envision because sedimentation clarity is that modeled value that encompasses lots of different things. And some of them can be controlled by humans, like channelization, and some of them can't, like the type of soil is something we can't change. But something that's much easier to visualize is the impervious parameter, where we see that a 10% increase in imperviousness would result in a 5.2% decrease in stream quality. So this is easy to envision because we can think of something like a field being paved over to becoming a parking lot, and now we have a quantitative way to understand how that change can impact water quality. Then finally, we have the observation of the relationship between poverty and stream quality, where areas 10% higher in poverty tend to have a 4.7% lower stream quality. And it's important to note that these relationships aren't necessarily causational, but rather an observation of the relationship. So we can say that in areas of high poverty, we tend to also see lower stream quality. So let's recap about how we addressed our research questions. First, we were able to show that environmental and social data could be used to build a model, and we used that model to predict stream quality across the entire Rouge River watershed. This is especially useful information because now we understand what water quality might look like without having to go and observe every segment of river in the watershed. Second, we were able to learn about different parameters that affect water quality in the Rouge River. We know that sedimentation, imperviousness, and poverty are all important in the story of water quality in the Rouge River. And we know that imperviousness is one variable that we do have control over. And this is something that Friends of the Rouge is conscious of. They worked to preserve water quality by planting things like rain gardens that are able to decrease the amount of impervious cover by making a place where water can infiltrate or pass through in areas that might otherwise be highly pervious, like a parking lot. But we can also give added information to Friends of the Rouge by letting them know that there's this relationship between the percent poverty and stream quality. So now they know that they can implant things like rain gardens or other ways to decrease imperviousness, particularly in areas of high poverty, and have potentially high impact on areas that have really low water quality. So this summer I did a lot more than just modeling. I had a lot of personal and professional growth as well, learning how federal research and non-for-profit work go. I learned a lot about spatial modeling, and I had some personal growth researching in some areas that I haven't been exposed to before, like working with citizen science and environmental justice work with those social variables. And I also had a lot of great mentorship and advice from my mentors. So a big thank you to Drs. Tim McGuire, Sally Petrella at Friends of the Rouge, Dr. Casey Godwin, Dr. Craig Stowe, and to everyone at Sigler for making this such a great experience. At this time, I can take any questions.
Thank you so much, Isabelle. Wonderful presentation. Does anyone have questions for Isabelle? Feel free to go ahead and raise your hand if you do, and I will unmute you. Well, I'll allow you to unmute yourself, I think is how it works. Okay, Ayumi, you can go ahead and unmute.
Hi, can you hear me?
Yes, we can hear you.
Thank you. Very nice talk. Thank you, Isabelle. I have a question. So can the model take account of any history of the variables, like the history of poverty data and what you said, imperviousness, or it's all instantaneous?
So in its current state, we have a couple of ways that we are considering history. Imperviousness, the variable that we used, is reflecting data from 2001, 2006, and 2016. So it's an average of those 3 time points because the data set that comes from releases data about every 5 years. So we're due for an update in that. And we were trying to use an average of that imperviousness data since we're using an average of the SQI as well. But especially for the social data, we were looking at information collected just in 2016. So that could definitely be updated with other Census Bureau information as that's released over time.
Thank you.
Thank you for the question.
Yes, thanks, Ayumi.